Hey guys, so today we're going to be covering section 5.5 on the topic of substitution. In section 5.4, we introduced what is known as the fundamental theorem of calculus, which related the definite integral and the area under the curve and the topic of anti-differentiation. Now, the fundamental theorem of calculus is probably the most important theorem you will get in this class, hence its name, the fundamental theorem. Now, this section, while it is not going to contain one of the most powerful theorems, it will contain one of the most powerful tools that you will get in calculus. Why is it so powerful? Because it allows us to tackle much harder integration problems. For example, if you consider all the examples we did in the previous sections, they were all relatively basic. Integral of sine or cosine, integral of a basic polynomial, things like that. Something we have explicit rules for. But that doesn't happen that often. Most times in practice, we will have to use this topic, substitution. This will allow us to tackle a much wider variety of functions when we want to integrate them, for finding areas under the curve, for relating velocity, position, acceleration, and a bucket list full of other situations where we would require integration. Because it's so important, we're just going to go ahead and dive right into it. Let's start off by asking ourselves this question. What is the derivative of sine of 2x? Well, the derivative of sine of 2x is just 2 cosine of 2x. But what if we're not asked to take a derivative? What if we're asked to take an integral? For example, what is the integral of 2 cosine of 2x dx? Now, we don't have an explicit formula on our derivative sheet where we can just work backwards. However, by this calculation, we can see that the integral of 2 cosine 2x dx is simply sine of 2x plus some integrating constant right there, that plus c. We have to tack on that plus c because when we differentiate this, that constant's going to go away. So when we integrate 2 cosine of 2x, well, we are not entirely sure what that constant can be. All we know is that there is a constant there, and that constant might be 0. So this was a kind of jerry-rigged example. I already had this equation up here. I knew to take the derivative of sine of 2x to get 2 cosine of 2x. Now that is not always the case. So the next question we want to ask ourselves is, how can we extend this idea to more situations? How can we tackle problems that we might not necessarily see this equation off the bat? All right, let's look at some theory. Consider this scenario. We start off with 3 differentiable functions, f, g, and u. And by differentiable, I mean we can take the derivative of f, g, and u in terms of x, such that the function f of x can be written in terms of the composition function g of u of x multiplied by the derivative of u of x. Now, that might look really confusing with all these f, g's, u's, du's, dx's all over the place. So let's tie this into the previous example to see this setup. In the last example, we had our f of x to be 2 cosine of 2x equal to our function g of x, which is just cosine, but evaluated at the function u of x, where u of x is equal to 2x. So here's our f of x, here's our g of x, here's our u of x, and then this 2 right here is going to be our du dx. So essentially, we took an initial function f of x and we broke it up into a composition of functions multiplied by the derivative of the inside. Now that phrase, derivative of the inside, that should ring a bell. Notice this seems to be related to the chain rule. And if you're thinking that, you'd be correct. Substitution is allowing us to kind of undo the chain rule. And by that, so let's take a look into the rest of this so we can kind of see that a little bit more clearly. So let's suppose we have this scenario. Then the integral of this function f of x is equal to the integral of g of u of x du dx times dx. So in short, take the integral of both sides right here. But notice we have a dx down here and a dx up here. They can actually cancel with each other. So we're just left with the integral of g of u of x du. And then from there, that integral is going to be capital G of u plus c, where capital G is the antiderivative of little g. And then we have our little integrating constant there at the side. So what this theorem is telling us is if we have a function f of x written in this form, when we integrate that function, it's really integrating this little g here and getting its antiderivative and evaluating it at that function u of x and tacking on our integrating constant. Now, if this is utterly confusing right now, just bear with me. Let's see a whole lot of examples on how to do this. So, rather than doing that approach where we started with taking the derivative of sine of 2x and getting our function, let's just use this theory and try and tackle the exact same integral as before. Just make sure. Okay. So, let's do this. Before we jump into this, let's take a second to kind of analyze the situation we are in. We are asked to take the integral of 2 cosine of x dx, or in short, find the antiderivative to 2 cosine of 2x. But before we just start integrating things and start guessing, let's look at this carefully. We have a 2 out in front, we have our function cosine of something, and in here we have our 2x. But we notice that the derivative of 2x is in fact 2. So we have the integral of some function, cosine of x, composed of another function, 2x, multiplied by the derivative of that inside function, which is just 2. But that's kind of a mouthful, so let's kind of write this down. Because this is kind of a lot of stuff, we're going to start renaming things. First, I'm going to call u 2x. I'm just assigning 2x a name. We're just going to call it u. But now we want a derivative of u with respect to x. So let's calculate du dx. That's just equal to ddx of 2x. But what is the derivative of 2x? Well, that's just 2. So that means du dx is just 2. But I don't want a du dx, I just want a du. So what I'm going to do is multiply du over dx by dx. But we do to one side, you have to do to the other, and we get the dx is right here to cancel. So we conclude that du is equal to 2 dx. So let's take a second and recap what I just did. I named this function 2x u. I differentiated it with respect to x, and then got du dx is equal to 2. And then I moved the dx to the other side, and we got du is equal to 2 dx. Now, why did we do this? We'll see in a second. This is what we call calculus magic, because when you do things like substitution, it seems weird and roundabout, but then you end up with the right answer, and you're just like, okay, how did we do that? Yeah, it's kind of like pulling a rabbit out of a hat. This is the calculus equivalent. So let's go relook at the original problem. The integral of 2 cosine of 2x dx. But 2x we renamed. We call it 2xu. So let's just write that in. So this integral is equal to 2 cosine of u dx. Now right here, we kind of want to automatically integrate this off the bat. Oh, we know what the integral of 2 cosine of u is. That's just 2 sine of u. That's just a basic property. But we have a small problem. Cosine is in terms of u, but we are integrating with respect to x. That's a problem. We cannot just integrate right here, right now, move on, call it a day. Cosine is in terms of u, but we're actually integrating with respect to x. So either we need to rewrite this in terms of x again, or we need to get a du in here instead of a dx. Now that first route, if we get this back in terms of x, we end up back where we started and we went nowhere. So now what we want to do is change this dx into a du. But do we have a relationship between dx and du? Yes, we do. It's this thing right here that we solve for. Du is equal to 2 dx. So now, here's the name of this tool, substitution. We're going to sub in du for 2 dx. To make that a little clearer, I'm going to rewrite this as the integral of cosine of u times 2 dx. Now, this 2 dx right here, that's just our du. So this is equal to the integral of cosine of u with respect to u. But now, what's the integral of cosine u with respect to u? Well, that's just sine of u plus our integrating constant c. But now our answer is in terms of u. We want our answer to be terms of x. We're working with functions of x. We want to end up with a function of x. So by subbing back in, we get sine of, what do we call u? Well, we called u 2x. So this becomes sine of 2x plus c. Now, if you recall, that's exactly the answer we came up at the beginning of the lecture. So this is the technique of u substitution. And if you're sitting there kind of with your jaw kind of open, relax. That's pretty much how everybody sees substitution the first time. It's this weird magic trick that you're not entirely sure what just happened, and you're very confused and you're a little scared. But bear with me. I have about, between this lecture and the next one, I have about 30 examples where we're just going to practice this over and over again. So just hang in there with me, and by the end of this, you're going to start feeling much better about this. Now, we could jump into a lot more complicated examples, but let's not do that. Here, we integrated to cosine of 2x. Now let's just integrate cosine of 2x dx. Essentially, we got rid of the 2 that was out in front. Let's do this exact same process again. Now, we know how to integrate cosine of x. It's that 2x in there that's giving us a problem. So that's what we're going to call u. So we're going to set u to be 2x again. But in the exact same way last time, we concluded that du is just 2 times dx. Quick way to do this. Take the derivative of the right-hand side with respect to x and then tack on a dx at the end. That's how you get du. Differentiate this with respect to x, you get 2, but then tack on a dx at the end, and then you get du is equal to 2 dx. That's pretty much how you get u and du. Now from here, let's rewrite our initial equation in terms of u. So we get the integral of cosine of 2x dx is equal to the integral of cosine of u dx. But there's a problem. The function we're integrating is in terms of u. However, this dx is telling us that we need to integrate with respect to the variable x. That's a problem. So this is why we have this equation right here. This du is equal to 2 dx. We need to introduce a du in here. So let's go ahead and do that. Well, I want to just write in du for this dx, but there's a problem. This 2. Du is equal to 2 times dx, but we only have a dx. We don't have a 2. So we're just going to go ahead and just write a 2 in there. So we're just going to go ahead and stick a 2 right here. Am I allowed to do that? No. No, I'm not. I'm not allowed to just stick numbers in places and just move on with my life. I mean, I can integrate this equation here right now. No problem. It's a shame that wasn't the question that was asked. So if I want to stick a 2 in here, I have to balance it out. You know what I've been saying all semester, that the most powerful things in math you can do are multiply by 1 and add by 0? Well, here's where we're going to multiply by 1. If I'm going to multiply in here by a 2, then I need to multiply out in front by a 1/2. Because what is 1/2 times 2? It's just 1. All I've done is change the form. I haven't changed the value. All right. So now I have a 2 dx inside my equation, and now I can do my substitution. So this is equal to 1/2 cosine of u du. Now here, this is just a straightforward anti-differentiation technique that we've seen half a dozen times so far. We just recognize that the derivative of sine of u is equal to cosine of u. So the integral of cosine of u is just sine of u. Now we get this 1/2 integral of cosine u du is just 1/2 times sine of u plus c, which is just equal to 1/2 sine of u plus c again. Now, why did I not put 1/2 c? Because half a constant is still a constant, and we didn't know what it was to begin with, so I'm just going to keep calling it c. It's kind of lazy, but it gets the job done, so we're good with it. So we are saying that the integral of cosine of 2x dx is equal to 1/2 sine of u plus c. But it's the same problem as last time. This is in terms of u, not x. Our problem was given to us in terms of x, so our answer needs to be in terms of x. So we're going to sub back in one more time, and we get that the integral of cosine of 2x is equal to 1/2 sine of 2x plus c. All right. So that's it for that example. All right. Now let's look at a little bit more complicated examples. Let's look at this one. The integral of secant squared of 3x minus 1 dx. Now, we know how to integrate secant squared of x. Well, the integral of secant squared of x dx is just tangent of x plus c. We know that. Secant squared of x isn't a problem. This 3x minus 1 here, that's our problem. That's our problem when we try to integrate. And since that's our problem, I'm just going to call it u. U is equal to 3x minus 1. So a way to think about it is u is the problem. Yeah, remember that. U is the problem. Now, we have our u is equal to 3x minus 1. But up here, we have a dx, so now we need a du. And we get du dx is equal to ddx of 3x minus 1, which is just equal to 3. So we can conclude that du is equal to 3 dx. Now this is probably going to be the last time I write this out in full like this. Next time I'm probably just going to go straight to writing it as such. Du is equal to 3 dx. But you're just taking the derivative of u with respect to x, getting your answer, and multiplying everything by dx. So I'm just going to skip that stuff from here on out. And we just get du is equal to 3 dx. And since I'm going to be skipping this step from now on, you can too. On exam with written work, you can just write u is equal to 3x minus 1, and du is equal to 3 dx. And since the title of the section is substitution, let's do substitution. All right, let's rewrite our initial problem, the integral of secant squared of 3x minus 1 dx. Well, 3x minus 1 we renamed. So this is the integral of secant squared of u dx. However, this is in terms of u, but we want to integrate with respect to x. We have to change one of them, but if we go back to x, then we went nowhere. So another way to think of that is, going back to your x's never works out. So let's move on and let's focus on u here, shall we? So we need to figure out a way to get du inside this equation. But the problem is this 3 right here, this 3 times dx. I really want secant squared of u times 3 dx. But once again, I cannot just stick 3's into places and move on with my life. I've changed the problem, so I mean, that's all fun, but you're really not doing anything that's useful. So we cannot change the problem. So we multiplied by 3 inside, we have to multiply by 1/3 out in front. We have to undo what we did on the inside. Now, we have 1/3 times the integral of secant squared of u times 3 dx. This is just equal to 1/3 times the integral of secant squared of u times du. Since 3 dx is just du. And now from here, we get 1/3 times the integral of secant squared of u with respect to u. But we know that the integral of secant squared of x dx is equal to tangent of x plus c. We get 1/3 times tangent of u plus c, which is just 1/3 tan u plus c again. I know, lazy, should be 1/3 the constant. However, it's just a constant, don't know what it is, so we don't care. We're just going to call it c and move on with our lives. Now, our answer is in terms of u, but we need our answer in terms of x. So we're going to sub back in for u, and we get our answer to be 1/3 tangent of 3x minus 1 plus c. And then this is our integral. Now, this did require some forehand knowledge. It did require knowing that the integral of secant squared of x dx is equal to tangent, or another way of putting it is that the derivative of tangent is secant squared. This is why we had that section 5.1 on anti-differentiation, where we introduced the topic of how to undo the derivative, and why I've been harping all semester that you really need to know your derivative rules. If you do not know that the derivative tangent is secant squared, this problem is going to be very, very hard. Okay, guys? It would be very hard. All right? So make sure that you know your differentiation rules with your trig functions, your exponential functions, things like that. Make sure you know those, because then integration will be a whole lot easier for you, since integration is just undoing the derivative. All right, so that's it for that example. All right, now I don't know about you guys, but I'm getting kind of tired of doing these trig functions, so let's change it up a little bit here, shall we? Let's try this one. Let's try integrating x times the square root of x squared plus 3. All right, now how do we want to tackle this one? This one is much different than the other ones we have done. So let's look at this. We have x right here, he's just chilling, and then we have the square root of x squared plus 3. Now, if this was just the square root of x, we could just rewrite it as an exponent, multiply it out, and then we just get x to the 3/2, and that's just a simple application of the power rule for integration. But we don't have that. We have this x squared plus 3 in here that is giving us a headache, because we cannot rewrite this as x squared plus 3 to the 1/2, distribute the 1/2, because we're not allowed to do that. That's a problem. We cannot do that. So this x squared plus 3 here, that's what's giving us a headache. Now right there, you might have thought I'm the one giving you the headache, but I promise you, it's not me, it's the calculus. I promise. So we have to ask ourselves, how can we tackle this problem? Well, that x squared plus 3 is giving us a problem, so we're just going to rename it. We're going to call it u. So we get u is equal to x squared plus 3. So du is simply 2x dx. All right, cool. That u looks like a v. So let's fix that. So du is equal to 2x dx. Now we want to do our substitution. So we get our original problem, the integral of x times the square root of x squared plus 3 dx. Well, that's just equal to the integral of x times the square root of u dx. Now here you might be tempted to multiply x and u together, integrating those rules. That's a big no-no. That's a big no-no. Because x and u are not the same thing. They're not the same thing. That's why we gave them different names. They're different things. And since we're just integrating with respect to x, that u is going to be a problem. So we need all the variables to be the same thing. We need to get rid of this x right here. That x needs to go away, and this dx needs to go away, and I need a du. Thankfully, I have this equation right here, equating du and dx together. But the problem is this 2x right here. We have the x, but we don't have the 2. So we need to introduce a 2 in there. So you can write this as the integral of square root of u times 2x dx. But I can't just stick 2's into places and move on with my life. I have to multiply by 1/2 out in front. Well, I'll multiply by 2, then I also need to multiply by 1/2. I have to undo myself. And why did we do this? Because du is equal to 2x dx, and now we have a 2x dx inside. Now we can continue on with our substitution and get 1/2 times the integral of square root of u times du. Now, this is starting to look like something that we can handle. So let's go up here for a little bit more room. Now, it's just a straight integration of the square root of u. Now, the square root of u, well, we can just write that as u to the 1/2. So we get 1/2 times the integral of u to the 1/2 du. So we have the integral of a variable to a power, and we're integrating with respect to that variable. It's just the power rule now. So it's equal to 1/2 times the power rule is add 1 to the exponent and divide by the new exponent. Tack on our integrating constant, which is equal to 1/2 times u to the 3 halves over 3 halves plus c. And then from here, what do we get? Well, that 2 and that 2 are going to cancel, and that's equal to u to the 3 halves over 3 plus c. And now we have it. That's our antiderivative. U to the 3 halves divided by 3 plus c. Now, this step right here that confuses you, how I could cancel out those 2's, shoot me an email, and I'll be happy to explain that in a little bit more detail. All right, so we have u to the 3 halves divided by 3 plus c. But we're not quite done yet. Our problem was given to us in terms of x, and our answer is in terms of u. So basically this problem is telling us that x is better than u, so we have to sub back in for x, and we get that the u to the 3 halves divided by 3 plus c is actually just 1/3, I just pulled the 3 out front, times u, but u is just x squared plus 3 raised to the 3 halves plus c. Now you might be looking at that and saying, no way that the integral of x times the square root of x squared plus 3 is just 1/3 x squared plus 3 to the 3 halves plus c. There's a very simple way that you can test it. Take the derivative of our answer right here and see if you end up with this. That's how you can always check your work when you're doing these integration problems. Take your answer, differentiate it, and make sure you end up back where you started. So I promise, if you don't end up back where you started, then there's either a problem with your integration or a problem with your differentiation. And since you've been doing differentiation a lot longer, I'd bank on your differentiation skills. So if they don't line up, check your work. You might have made a mistake somewhere in there. All right, so that's that example. But let's see another kind of example. How about an exponential? When we have the integral of 2x squared times e to the 4x cubed plus 7 dx. All right, so this exponential function, this is the most different kind of example we've seen so far. We've seen the trig ones, and then the polynomial style looking problem as before, basically just x to some powers, multiply things together. Pretty straightforward here. But this exponential, this is a little bit different. Now, I would like to remind you of this rule, that the derivative of e to some function of x is just e to that function of x times the derivative of that function of x. It's a very neat property. It's something we love about exponential functions with base e, because the derivative with respect to x of e to the x is just e to the x. We love that property. We really do. But this part right here, this chain rule step where we have to do this, in fact, when we're integrating, is actually kind of a headache. It's like that person in class that tries too hard to be helpful, but it actually ends up just kind of giving you a small little headache. That's what exponential functions are in integration. When we have e to some function of x right here, that's our problem. Like it means well, it has very nice properties, and we really love having it around, but when we're integrating it, it kind of gives us a problem. So we have to be pretty careful when we deal with integrating exponential functions. The integral of 2x squared times e to the 4x cubed plus 7 is not just itself. It's not just e to the 4x cubed plus 7 times the integral of 2x squared. We wish it was. That's not how it works. But to tackle this problem, we have to use our good old buddy substitution here again. So if we look back over here at this derivative of e to the function of x, we look at this, we get e to the f of x times the derivative of the exponent. So if we're kind of thinking about undoing this process, it's this guy up here, this function of x, that's kind of giving us a little bit of a problem. It's what e has been raised to. That's the situation we want to handle. Just like in this problem, where it was the thing under the radical, that x squared plus 3 that's giving us a problem. Now, it's the 4x cubed plus 7. That's what we want to sub out. Now, the thing about substitution is, the integration itself is usually not too hard. Not if you did your substitution correctly. Then the integration step is usually not too terribly difficult. In substitution, it's the choice of u that matters. If you do a good job at choosing your u, then the substitution is going to fall out nicely. But the only way to get good at choosing your u is practice. That's really the only way to get good at substitution, is practice. Eventually, you're going to be able to start looking at these problems and recognizing what you need to sub in and out. But until then, it's just trial and error. So you kind of have to prioritize. What is most likely going to be my problem when I'm integrating? When you have radicals like this, a lot of times it's going to be a thing under the radical. And we're dealing with these exponential functions, e raised to some function of x. It's a good chance that it's going to be that exponential function, that 4x cubed plus 7. That function in the exponent is probably going to be what you're going to want to sub out. And the only way to check to see if what your choice of u works is to do the problem and see if you get anywhere useful. So that's what we're going to do. Let u equal 4x cubed plus 7. Then we get du is 12x squared. All right, cool. dx. So now we're cooking. All right. So we have u is equal to 4x cubed plus 7, and du is equal to 12x squared dx. So let's go ahead and start subbing out things that we can. Let's go rewrite our initial problem, the integral of 2x squared e to the 4x cubed plus 7 dx. Well, this is just the integral of 2x squared e to u times dx. But now we have two different variables, so now we need to get rid of all the x's. But this dx in here requires us to have this term in here, that 12x squared. Now we already have 2x squared. We already have a good chunk of it, but we don't have the 12. So we need to turn this 2 into a 12. Now how can we do that? Well, the first thing that comes to my mind is multiply it by 6. So we take 2x squared, multiply it by 6. So we get 6 times 2x squared times e to the u dx. But the problem is, if I multiply by 6, I also have to multiply by 1/6. Now you might be asking, why on earth did I multiply by 1/6 and 6th? Because if we simplify, this equation turns into the 1/6 times the integral of 12x squared e to the u dx. And right here, 12x squared times dx, that's exactly what I need for my du. So I can rewrite 1/6 the integral of 12x squared eu dx as 1/6 the integral of e to the u times du. Because du is equal to 12x squared dx, and here I have my 12x squared dx. Now I'm integrating a function of u with respect to u. Now we get to use the very nice property of e to the u. We get to use this guy right here, that the derivative e to the x is e to the x. So the integral of e to the u times du is just, wow, that was a horrible 6. That looked like an epsilon. Good Lord. So we have 1/6 times the integral of e to the u, but that's just e to the u plus c. The reason the integral of e to the u is just e to the u, because the derivative of e to the u is just e to u. Now is where the niceties of it come into play. So we get 1/6 times e to the u plus c, which is just 1/6 e to the u plus c, because we're lazy and we're not going to write 1/6 c because a constant's a constant, so we don't really care too much. But the problem was given to us in terms of x, so we need to answer in terms of x. So we need to sub out this u right here, and we get this is equal to 1/6 e raised to the, what do we put, 4x cubed plus 7 plus our integrating constant. Now, I might be a little hand-wavy in multiplying the constant by another constant, but I'm always careful of tacking on that plus c. That plus c has to be there. Whether you write 1/6c, 17c, pi c, it really doesn't matter. As long as you have that c there representing that integrating constant, you're good to go. So, quick recap. We recognize that this 4x cubed right here was kind of giving us a problem in our integration step. So we let u equal 4x cubed plus 7. Then we calculated du is equal to 12x squared dx. We did our substitution process. We ended up over here. And then we got to use our nice property that the derivative e to the x is just e to the x. We integrated here, sub back in, and we get our answer as 1/6 e to the 4x cubed plus 7 plus c. Don't believe me? Take the derivative of this guy and make sure that you end up with 2x squared times e to the 4x cubed plus 7. All right, I think that's where I'm going to call part 1 of this video, and we're going to pick off with the next example in part 2.